Part 2 of the Chapter 13 homework, and I just realized this problem was in both parts, so you don't really need to do that. Anyhow, you can listen to Part 1 if you want that solution. For problem 24, what we've ended up having is a Goodyear blimp. Its volume is 5,700 cubic meters of helium, and it says if the envelope and the gondola have a total mass of 4,300 kilograms, what's the maximum cargo could hold at a sea level location if the air temperature is 20 degrees Celsius. So basically, we've got to find all the buoyant force, which is causing it to lift up due to the density of air and helium, and then the whole weight going down. So the part that's a little tricky here is there's the force of gravity on the mass that we know about, which is due to the mass of 4,300 kilograms, the envelope in the gondola, but there's also the weight of the helium here. So I don't think they meant that was already included. So we have to think about that. So the buoyant force is basically going to be the weight of the air that is displaced. So that is 1.2 kilograms per cubic meter, 5,700 cubic meters, 9.8 newtons per kilogram. So it's about 67,000 newtons. Now, gravity acting on the helium is 0.166 kilograms per cubic meter times V times G. So that's 9,273 newtons. That's the weight of the helium. So that means that right now the lifting force would be 57,759. That means the lifting mass would be 5,894, but the mass is 4,300. So subtract that off so you could carry about 1,600 kilograms of cargo. Now, I did this a little bit weird. Like I said, I kind of mixed masses and forces. You just want to be careful within a calculation not to mix them at that particular point. So here I had forces. I got my net force basically upward, or not the net force upward. The net buoyant force. So this is the buoyant force, and that's the mass of the helium. And then I divided that by 9.8 to get the mass up equivalent upward, weight downward. That was a little weird. For problem 25, hey, somebody's messaging me at this point. We've got a block. It's an ethyl alcohol, and it said that the block was 100 cubic centimeters of aluminum, and you want to find the tension in the string. I really like doing free body diagram for this because it helps me out. So aluminum is more dense than ethanol, so it would otherwise sink, so there has to be some tension on the string. So gravity down on the aluminum, buoyant force up on the aluminum, tension up on the aluminum, those should be equal to each other. So I'm changing this free body diagram into this equation. Well, how do I find the buoyant force? It's rho times V times G, V being the volume of liquid that's displaced. We were told that it's 100 cubic centimeters, but I want to convert that to cubic meters. It's not as simple as you think. It's not just moving the decimal over two places because we're talking about cubes, cubic measurement. So that is 0.0001 cubic meters of volume. So that multiplied by the density of ethanol times 9.8 gives us the buoyant force. That's about 0.7742 newtons. It's not about, that's exact. Gravity acting on the aluminum, that's the density of aluminum. That's the volume, times 0.8, 2.646 newtons. So the difference between those would be the tension, and that's 1.87 newtons. For problem 35, this is an example of, again, so the 1 centimeter pipe widens to 2 centimeters, then narrows to 0.5 centimeters. The liquid flows through them. What are the at 4 meters per second at first? What are the speeds in the second and third segments? Well, you can think about this proportionally if you want. Technically, the continuity formula in terms of the volume flow rate, pi r squared is the area times the speed. Well, technically, these are diameters and not radii, but it's proportional. So again, here, the radius would be 0.5. The radius here would be 1. 0.5 squared is 0.25. 1 squared is 1. So it's still a 4-to-1 ratio. So essentially, I can say this would only be going 1 meter per second in the wider area. Same thing here in the narrower area. pi r squared v. So it's going to be going 4 times as fast. And I talked about that a little bit. The volume flow rate, here we do need to use pi r squared. So 0.005 meters squared times pi times 4 meters per second tells me I get 0.000314 times 10 to the meters cubed per second. I was combining my scientific notation and decimals, so that's the amount you get. 37 is a Bernoulli's equation, so you're trying to find the pressure at the top gauge. We first need to find the volume flow rate. No, we don't. That's what I thought I might have to do, but we do not. So we're using this big long equation again. We're told this. We know this speed. We know this speed. We know this is 10 meters above. So I'm going to put this pressure in. The density, it's oil. So again, that from table 13.1 on page 442 is where I got that. Should probably say that. I'll make that smaller. So this is the lowest height, so I can just cross that out. That's going to be 0. 1/2 density times v squared equals P2, which is what we're trying to find out. Rho GH, 1/2 rho v squared. I like to show all these different parts here before I add them up. And I end up getting at P2 would be 109,600 pascals. The last one here is actually pretty tricky. I thought that's number 65. And it's got a pipe flowing with water in down here, out up here. It gives you the area and the area, so you don't need to do a pi r squared thing, although they're in centimeters squared instead of meters squared, but it would again be proportional to each other. So at this particular point, you want to find the pressure as the water exits to the air. Well, it's air pressure. So that's 101,300 pascals. So that is that. Find the height of the standing water column. Okay, so this is where we have to use Bernoulli's principle. And therefore, that means that's going to allow us to find the pressure down in this region, and that'll let us know for this area where the water is still how high the water or the liquid would have to be. So it is water. So I'm going to use the Bernoulli's equation here. We're trying to find P1. We know that at this particular point, there's no height at that point. We're going to call that 0. So 1/2 density v squared equals atmospheric pressure at the end, rho GH plus 1/2 rho v squared. So that gets me at P1, which is somewhere down here, 141,500 pascals. So then the question would be, what standing column of water up here would also end up getting you 141,500 pascals? Now that is an absolute pressure, by the way, because this is an absolute pressure for the atmosphere. So that means that the extra pressure caused by the water column would be 45,200 pascals rho GH. So this height is 4.6 meters. So kind of interestingly, this height is above the end here. Hopefully that kind of makes sense because the water is still moving here at a lower height. So we have to have enough pressure to cause that to happen. This is a tricky problem. Anyhow, hopefully those help, and those are your solutions to part 2.